Thank you for, it's very nice to be here. We started with a very interesting talk, and we will have more in today and tomorrow. So my topic, the thing that I will be discussing today will be black hole entropy or black hole thermodynamics in high derivative theories of gravity. But most importantly, what I want to highlight is that in my talk, I will try to convince that we will be looking at off-cell structure of classical equations of motion following from arbitrary diffeomorphism invariant Lagrangian, and that will be an universal statement of any theory of gravity. We will add matters and all, and then we will from there understand what we can learn about classical laws of black hole thermodynamics, and at the end I will try to discuss some work that we did very recently on understanding entropy and area bounds, which are known as covariant bounds or covariant entropy bounds or Busso bounds. So throughout my talk I'll be talking about classical gravity. There will not even be any quantum matter, so no Hawking radiations or anything. We will be discussing, I should mention black hole mechanics and not thermodynamics. So these are based on some works which we have been doing in past few years, and they are my collaborators, Shayantani Parthajit, who is a postdoc at Belur, Pratex, he was a student at IIT Kanpur, now a postdoc at University of Victoria. Shuvayu is a postdoc now at Gandhinagar. Jyotirmoy, Milan, I think here, Anirban and Ishan was undergrad at IIT Kanpur. Our work will crucially depend on works done by Aaron Wall, Sudipto Sarkar, Harvey Riel, Ian Davis, and many other people, which I will try to mention. So please feel free to stop me at any point if you have any question. Some of you, I can see, have already heard some parts of it, so please excuse me if you don't get anything new here. So first let us understand how off-cell structure of classical equations of motion are going to be important for black hole mechanics. Now black hole mechanics or black hole thermodynamics is well known in general relativity, and we know black holes behave like thermodynamic objects, but by which I mean that some geometric notions can be attached to thermodynamic properties. For example, area is known, area of the horizon gives us the entropy and stuff like that, and there is also an understanding that GR is not a complete theory, because if you have any UV complete theory of gravity, they will generate corrections to derivative theory of gravity. So for example, at the level of the action, if we have this two derivative Einstein's GR, and we will be getting high derivative terms in the Lagrangian, so we will be, and also from a gravity or a GR perspective, it will be interesting to know if black holes are still solutions of such kind of theories. What do we know about their thermodynamic properties? Now there is a well-known definition of entropy for black holes in high derivative theories of gravity, or in general any diffeomorphism invariant theory of gravity, which is known as the world entropy. And this is also geometric in a sense that if I am given the Lagrangian, by this I can compute the entropy, but this was by construction was applied to stationary black holes. So only the first law was known to be, well, that was the consistency condition with which this definition was derived, and obviously it reduces to the definition of area of a black hole in Einstein's GR. Now, for out of equilibrium or non-stationary black holes, world entropy suffers ambiguities, which are known as Jacobson-Keng-Myers entropy. So what do I mean by that? So, I mean, I can add, sorry. I can add those terms here, and they will satisfy the first law. But these JKM terms can be added, but they will become 0 if I take the stationary limit. Now the question that we want to ask is, can we find an entropy and geometric definition of out of equilibrium black hole entropy, which will probably satisfy the second law, for which world entropy was known that it's known that the world entropy doesn't satisfy the linearized the second law.
So
yes.
Educated, but epsilon
These epsilons are binormals to the codimension 2 slices. The binormals. The binormals of the.
And also just to clarify, you're not allowing non-local terms in your Lagrangian.
Non-local terms like
R 1 over box R.
No. Although I'm not sure if, well, I've not studied those terms. I mean, I don't know if these will, what we have done will go through or not, probably or not, but we have not looked at them. Now, sorry. JKM term will be 0 on the bifurcation surface, yes. But if we are out of the bifurcation surface, then we can have them.
So those terms are ambiguous is the statement, or they are those are
If you just think from the first law point of view, they are ambiguous. This world entropy definition is ambiguous.
world entropy or the SJK? Which one is ambiguous?
I mean, I can add SJKM. These SJKMs are like these extrinsic curvatures of the codimension 2 surfaces. So I can add them with any coefficients, let's say. So one of the job will be to kind of find if I can use this the second law to be a condition or a restriction to fix these JKM pieces. That's what we will be doing.
The JKM terms in the original papers were fixed by demanding a consistent Dirichlet theory, theory with Dirichlet boundary conditions for a Gauss-Bonnet gravity.
I see.
So you require to have those specific terms, squares of the extrinsic curvature.
Squares of the extrinsic curvatures.
Find way to get the equation of motion.
But they are not like
They are the analogs of the Gibbons-Hawking.
Gibbons-Hawking terms. But I think here the Gibbons-Hawking term, I mean, for example, the Gibbons-Hawking term should be there for even the stationary case, for that matter. But here the JKM pieces are, I think, different in the sense that they will vanish if you take the stationary limit. So the definition will.
You just now said that you can put arbitrary coefficients in front of the extrinsic curvature square term, but I don't think that is true.
Arbitrary coefficients at the level of, if I am taking the first law, I meant. But the linearized second law or non-linear second law will fix them. We will see how it comes.
You won't get a well-defined way to get the equations of motion if you don't have specific coefficients. Because when you're doing the variational principle, you require to cancel the boundary terms.
Yes, but the local equations of motion that we generally obtain from, let's say, root gr, r mu nu minus half g mu nu r. I mean, I'll be working with those kind of equations.
I mean, when you have high derivative high derivative corrections, you are going to work out the equation of motion with the high derivative corrections, right?
With the high derivative terms.
So that means that you are implicitly assuming that there are well-defined boundary terms which cancel.
I'm assuming, yes. We will not use them explicitly. For example, the Gibbons-Hawking term for root gr, we know that they should be there, but for finding solutions, we don't need them explicitly at the level of finding solutions.
Sorry.
Yeah.
If you just had the world entropy, would it satisfy the second law?
No, one can show that can violate the fails to satisfy the second law. One can find a configuration for which that will. Now, what type of theories do we consider? So when I say diffeomorphism invariant Lagrangian, I generically mean that the gravity Lagrangian can be functions of the metric, the Riemann, the symmetrized derivative of the Riemann, and any of them, any number of them, and contracted appropriately, so that ultimately I have a Lorentz, I have a scalar over here. We will also look into, we have also done extended our construction to non-diffeomorphism invariant Chern-Simons theories. They are diffeomorphism invariant up to total derivatives. For example, in 2+1 dimensions, I can have a pure gravity Chern-Simons term. In 4+1 dimension, I can have a gauge gravity mixed Chern-Simons term like this, where I can kind of go from this description to this description up to a total derivative term. So sometimes and also we have seen, like, in all higher dimensions, whatever Chern-Simons theory we can write down. We will look into matter couplings. So our results will apply to matter couplings. So for example, this is kind of a minimal coupling. This will be a minimal coupling, but this term will be a non-minimal coupling. If I take my G mu nu to be the eta mu nu flat space, this kind of coupling will not survive. So they are the non-minimal kind of coupling. So our results will apply to any of such kind of non-minimal couplings as well. And sometimes we will be discussing effective field theory setups, by which I mean that I will have a leading two derivative theory of gravity, but then I can have our derivative corrections with some dimensionful numbers to take care of the dimensions. Probably this should be alpha square, or if this is a length, should be length to the twice m, so that the length dimensions over here are the same as 2. So and we can treat these alphas to be small. So these are kind of the theories where our results will apply. Now, what is the physical question that we are trying to answer? So we will start with a stationary black hole, which will be perturbed by some external energy momentum tensor, and it will finally settle down to another stationary configuration. Now, we would like to ask whether entropy increases in this process. Now, that can be of two types. So I can talk about the difference between the final entropy and the initial entropy, or we can ask about a local question, whether entropy increases at each instances. So we will be looking at it in the second way. We will ask whether it increases at every instant of time, from going from stationarity 1 to stationarity 2. And
If you're treating alpha to be small, won't it always be dominated by the first?
we will come to a situation, actually. We will come to a situation. Yeah, so just to give you the answer, so we will be looking into stationary black holes perturbed by small amplitudes. Now there are two small parameters now, the amplitude epsilon and the alpha. So we can find configurations where there will be some interplay between them, so that even though they are kind of, for example, this will be very important for the Busop bound kind of thing, where I will come to.
You have some notion of kind of which horizon will you be computing the area or area envelope of? Because is the apparent horizon?
So we are ignorant about that. So far, we are kind of looking at killing horizons, and we are assuming that the event horizon, although it's a teleological thing, it's an event horizon. But recently there has been approaches to look into apparent horizons, but we have not done that. So we will look into killing horizons.
So just the final, you'll take the final event horizon like you normally do in the
Yes,
system,
yeah.
and then you trace it back and check along.
Yes.
Okay, thank you.
Now, in 2015, there was a proof which kind of argued this linearized second law. So linearized mean I will treat the perturbation, the amplitude of the perturbation, up to linearized approximation, which is local in time, but it was integrated over the spatial slice of the horizon. Now we constructed an entropy current on the null horizon with non-negative divergences. So we are arguing for a second law which is local in both space and time. physically our result signifies that entropy is not just generated or destroyed, but if you look into a local element of a spatial cross section, there can be in or outflow, just like the continuity equation. So del rho del t plus divergence of j, we are kind of trying to talk about that j spatial component over here. Now we have to choose some gauge. So the near horizon geometry of any black hole, any dynamical black hole, can be written in this gauge. This is kind of a Gaussian normal coordinates. It can be written in this gauge where this r equals to 0 is the horizon. So the v is the affine null coordinate along the horizon, and xi's are the spatial coordinates, d minus 2 of them, and this r. So this has a very particular form in the sense that the coefficient over here is r square rather than r, but that's just a demand that r and v both we have chosen to be affine. So one can show that this is exactly the near horizon geometry of any dynamical black hole, which we will not work with any particular solution. We will at some point use that they are solutions of equation of motion. We will assume that they are solutions. We don't have to work with any given metric of the black hole solutions, but we will demand that whenever we get a solution of a given theory, that solution, the near horizon part, can be written like this, and then we will see how to use that. At least the near horizon part. For example, the near horizon part can be written like this. So this x omega I hij, they are metric coefficients and can depend on coefficients like this. Now a stationary black hole will be where we have a killing vector which becomes null on r equals to 0. So r equals to 0 over here will be a killing horizon. And for that, this x omega I and hij cannot have arbitrary functional dependence. It will become a function of r and v together, the product of them. So this one can check that this is the with this kind of a metric, and this xi given like this, this Lie derivative vanishes at r equals to one can check that. And then the perturbation will be like treated like this, where I will have the stationary black hole given by this configuration, and then I can have fluctuations or perturbations in the metric given by some small parameter epsilon, and this epsilon we will treat to be the small parameter when we are in linearized order, or epsilon square when we are into the next order. And you see the functional dependence over here, they are arbitrary r and v, but here they are just product of r and v. Now this stationary black hole has kind of a symmetry which so this is the killing symmetry, but this killing symmetry actually generates this boost transformation, which r going to lambda times r, v going to v by lambda with lambda constant. This metric is invariant, and this kind of are shown here with the green lines over here, and the non-stationary perturbations that I talked about over here, they will break this killing symmetry, but we can treat them in a perturbative manner. Now our main result about the off-cell structure of classical equation of motion for any diffeomorphism invariant theory of gravity, once written in that gauge, is the following: that the action, if we have an action like this, so from that action, if I obtain the equation of motion and I take the v component, which is like null projected component of the equation of motion, from the gravity part r and alpha hd, I will get some straight EVV, and the TVV will come from the L matter, and this EVV will have a structure like this. This is our main result. Whatever we do this using this was done before, was being done. How we go from here to the second law, how we go from here to the Busso bound, that's not something what we did, but this thing I feel this is what is the main result, and this is beyond any intention to study black hole thermodynamics or anything else, if I have a killing horizon and I perturb that the way I have described, the linear order piece, the order epsilon piece of the equation of motion evaluated at r equals to 0 when we wrote it in our gauge can always be written in this form.
Capital T, V and TI are not yet specified.
This capital T?
No, the guys inside.
This, I will say this is the definition of JV and JI. For example, this J, I will see what they will be. But as you can see, this is already kind of a divergence of an entropy current. That's what it's going to be, and that's how we will say that the equation of motion, the off-cell structure of it. I have not yet put EVV equals to 0 and solved for x omega I or Hij. I'm saying if you give me any Lagrangian, which can be anything of this form, the equation of motion and the VV component of it evaluated at r equals to 0, keep only the order epsilon pieces, will always be written like this. And we have proved in our paper in an abstract, with abstract arguments. And we have also checked them with several examples. Yes?
TVV gets contribution only from the matter part, or?
For now, my matter is minimally coupled. So this TVV is straight, but I will come to the non-minimal case.
Positivity condition or something?
As of now, it's not it's not needed. But as you said, if I go to the second law of black hole thermodynamics, that's what I have to do.
This equation will not be same if you allow the non-minimal coupling of it.
That's what our result will be. Just wait for some time. I will come to that.
I'm really sorry. R equal to 0 is the event horizon.
R equals to 0 is the event horizon in this metric. Now, killing. But for the black hole case, when we go to black hole thermodynamics, we will assume that to be our event horizon, future event.
Presumably there, it will be the event horizon.
It will be the event horizon.
In general, this statement is
In general, our statement is about killing horizons. That's what I'm saying. It has applicability. So I only needed that this is a killing vector at r equals to 0.
That's what's slightly confusing me. Sorry, let me ask you this, because you are interested in dynamical situations, right?
Yes.
Changing.
Yeah.
So let's say you had one of these higher derivative theories and stuff fell in, and things change around. Finally, it settled down to a black hole with an event horizon, right? Now I'm going to go back, I thought, like we do in the usual second law, along that null ray and ask, did the area or correspondingly whatever quantity increase or not, right? Now, that null ray is not a killing horizon.
If I really talk about black holes, dynamical black holes, there one needs to talk about apparent horizons and stuff like that. But one way of looking at it is, at any point I can do some coordinate transformations and bring that r equals to 0 to be that point. But I accept that criticism that one should really look at apparent horizons and otherwise.
If the black hole asymptotically really has time-like killing vector, then this Rax-and-Wald theorem will tell you that it will have a bifurcation surface in the past.
But whether they are all proven for high derivative theories. The rigidity theorem or whatever you are talking about, that there will be a bifurcation surface and all, that's what will be questioned. So we are assuming those things when we are kind of making those statements about black hole.
You must go, just to understand, maybe in that case, along as the system evolves, the event horizon won't be the killing horizon, right?
The event horizon is
Not a killing horizon, right? So I'm just, if the result is tied to the killing nature, then we will apply along the null ray corresponding to that. That's
Yeah.
all. Okay. Anyway, please go. Sorry.
L matters is to satisfy some energy conditions.
As of now, no, but as I replied to Chetan, that will have to be null energy condition. We will see why. As of now, it's just a statement that you can ignore the matter part. I'm saying whatever gravity Lagrangian you give me, that will have this structure. Even for Chern-Simons theories, which is like this. We have shown that this will also be the situation, and this is just an example. I mean, we have argued that if we have Chern-Simons theory abstractly argued in any odd dimensions, this will still be true. And now we will have to assume the null energy condition in TVV. So TVV is greater than equal to 0, but I am assuming at this point that equations of motions are satisfied, so EVV is equals to 0. This total EVV has to be 0, so this EVV, this straight EVV has to be less than equal to 0, which gives me this condition. And then if at the future the black hole settle down to equilibrium as it goes to 0, as we going to infinity, so the thing within this third bracket is a monotonically decreasing function of V, and it approaches 0 as V approaches infinity, so this thing should be greater than equal to 0. So this signifies that if I have some entropy current associated with the dynamical black hole whose time or the null component is this and the spatial component of this, so this is saying that the divergence of entropy current will be greater than equal to 0. So this is what I meant, that after we have proven this arguments leading to the second law is well known. We are just applying it to arbitrary theories of gravity by showing that the off-cell structure has this form. And sorry.
This is what you meant by having a purely classical matter, because otherwise it's very easy to violate null energy.
We'll come to yeah. So we were not doing anything quantum, but we will see probably in the next slide.
But is it true that in no classical situation I can violate null energy concept?
Yes, I can violate. I will come with non-minimal coupling. So I showed you this, but then this is another thing one has to prove, that this JV and JI are indeed associated with black hole entropy. So through this equation, this JV and JI gets defined, but what do they have to do with the entropy density or entropy flow density of a black hole? So that also we have been able to do. I'm not showing you here. So indeed this JV turns out to be the world entropy plus the JKM ambiguity is fixed. And this JI signifies the spatial flow of entropy on constant V slices of the horizon, and it vanishes on stationarity. Now in all the previous constructions, this equation was integrated on the constant V slices and compared between the initial V slice and the final V slice. So now if you take this equation and integrate it, you see you will lose this JI piece which we are saying. So you will compare the difference of this integrated quantity from here to here, and that's how even in 2015 when Aaron Wall gave his proof, he always used it with this integration on the constant V slices. So that's why we say that the construction that we are having is local in both space and time.
Does his proof is it easier to generalize to apparent horizons?
No, not done yet. Very recently, Wald has done some dynamical corrections said about in his earlier work, which says that this JV, when you evaluated it at that dynamical correction, that is actually the entropy of the apparent horizon, but only in root GR. It's like maybe a few months back, 5 or 6 months back. Now, non-minimal coupling, I think, sorry.
Just in the metric you've shown us, if you were sitting at R equal to 0, is that a null ring or not? It's not a null.
At R equals to 0, this is a null manifold.
Is it a null manifold?
Yes, it's a null manifold.
Okay, because just once, can you show the metric? Just once. So sorry.
Yeah, here maybe, or
Yeah.
here.
But if you're going at R equal to 0 and moving along the mean, it's a null manifold. So is that the event horizon traced back?
Well,
Or no? Am I confused? Okay, no, go on.
yeah.
I'm just trying to figure out what geometrically
local,
are
local portion of event horizon trace.
Local portion of, yeah.
R is away from the event. R is
R go-
coordinate
That's
and
what it
away
is,
from
right?
the event.
So then you really are going, you have your asymptotic event horizon and then you are going back along that manifold, right?
Yeah.
Okay, so that's how we normally.
That's how we normally do, but generally people say whether you can at all have a null surface and then it's an apparent horizon versus that discussion. We have not gone into that details.
That's fine. I mean, the apparent horizon is a different thing, but I'm just saying when we normally prove the second law and do
Exactly this one. This is how this is exactly, I would say, this part is exactly Hawking-Penrose area theorem. Okay.
The linearized version of that.
A linearized version of that. Yes, I agree. I'll come to that. We have made some progress. Other people also have made some progress. So coming to the non-minimal coupling case, if you have a non-minimal coupling like this, for example, let's take this as an example. The matter stress tensor that you get, let's say I had some minimal coupling, I will get T mu nu from there. If I have a non-minimal part in my Lagrangian, I will get a T tilde. Now the T tilde VV component, for example, for this has an order epsilon piece. Now if something comes with an order epsilon multiplied to it, the sign of epsilon is in my hand. I can choose perturbations where epsilon is negative, so I can easily make it negative. So these terms are problematic even classically for our proof that null energy condition has to be satisfied. But most importantly, what we have been able to show is that, how much time do I have?
15.
Okay, what we have been able to show is that this order epsilon pieces, whatever order epsilon piece you can get from any non-minimal coupling that you can write down, can also be written like a entropy current form. Now, if you have done that we have managed to cure this problematic order epsilon pieces by showing that they will always be of this form. So they will just add to the geometry part. So here I will say, if you have a non-minimal coupling, it's kind of confusing whether you have it's a matter Lagrangian or it's a geometry Lagrangian. But we are getting kind of a hint, at least operationally, that remove that order epsilon piece from here, club it with this, and this should be my new world entropy and the current. Now the question is, we have not checked it, is there a meaning to this ad hoc subtraction of order epsilon pieces? After leaving out the order epsilon pieces, whatever is remaining, first of all, if it has to qualify as a stress tensor, it has to be conserved. So we are checking it now, and preliminary results in some models shows that that itself is also conserved if you throw out the order epsilon piece, and it has to do with what this difference is, has to do with the way you define energy when non-minimal couplings are present. One way of defining energy is through the Noether process. You calculate the T mu nu, and the other way is take the Lagrangian and do a del G mu nu of that. They need not be the same always, and in non-minimal coupling case they are not the same. There are ambiguities, or what we know as the improvement terms or the Bell-Infante terms. These order epsilon pieces seem to be, so far in some models, are such kind of pieces. We have checked it in some cases and we would like to make it more precise. But at the linearized order level, linearized second law, this will go through now even with non-minimal coupling.
So the non-minimal coupling you have only checked for that example?
No, any non-minimal coupling, order epsilon pieces will always be written like this. So here are some examples I'm giving. For example, Einstein theory, if you do it in a brute force manner, you will get JV equal to 1 and the JI is 0. For R square, R mu nu square, you will get JV and JI as given here. And as you can see, this K bar, this Kij, K bar Ij, they are extrinsic curvatures and they were the JKM pieces, which now comes with a fixed number over here. And it came out of just writing the equation of motion in this form. And similarly for non-minimal coupling theories like this. For Chern-Simons theories, one can do a brute force calculation with this Lagrangian and show that the EVV is of this form, with JV being this and JI with having some structure. Yeah. Here? Oh, the order epsilon was the perturbation of the stationarity.
Statement is very important, and a term which is coming from the non-minimal coupling can always be written as a divergence of some.
Of this form.
Yeah, but this is a true you're saying in leading order, right?
In order, the order epsilon piece only. Because the order epsilon piece was problematic for the null energy condition, so we thought let's look at that, and we have shown that the order epsilon pieces, so there will be no order epsilon pieces remaining in the stress tensor. So, well, I'm not saying the rest of it will satisfy null energy condition. You can find out, I have cured the epsilon sitting in front, but maybe you can find a configuration for which even a positive epsilon times whatever, epsilon square times whatever you have involving del mu phi, let's say, are negative. That is there, that possibility is still there, but this violation was at our face and we could cure it like this. Now, we have not checked it, but at order epsilon order, it definitely there is an order epsilon piece. I mean, these calculations are, it's not possible to do by hand. Now I have told that there are things like Cadabra and we're trying to learn, and if we have to do anything beyond, probably.
You have to identify case by case, or is there a general?
Exactly, I'm coming to that. So this is not just a brute force approach. We can go through the covariant phase-phase formalism of Iyer and Wald, and we can find an independent definition of JV and JI through what we know as this presymplectic forms or this Noether Q mu nu. So this is actually the equation that we have, where U mu nu, xi nu is the killing vector, Q is the Noether current, and theta is the presymplectic potential, which is the total derivative term you get when you vary the Lagrangian. Now from this equation you can go ahead and obtain this JV and JI in terms of theta and Q. So if you give me a Lagrangian, I can put it in a computer and ask it to compute the presymplectic potential and the charges Q mu nu for me, and from there I can obtain the JV JI, and I can do a brute force calculation where I have to keep track of which is an order epsilon piece, which is an order epsilon square piece, throw the order epsilon square piece, organize them in that JV JI piece and get the JV JI, and we have checked in all the examples that we have worked, they matches. Now this is certainly not unique. This is certainly not unique because EVV equals to this. I can always add some JV star and JI star to JV and JI, which are of this form, which is actually 0 by itself. And we know there are ambiguities in this formalism which are known as the Iyer-Wald ambiguities. For example, if a Lagrangian changes by a total derivative. In this definition, I can add an antisymmetric tensor to theta and nothing will change. And then in this way, the definition of Q also suffers. So there is these 3 sources of ambiguities in the covariant phase-phase formalism of Iyer and Wald, and and using them, one can actually show what are actually the ambiguities in the entropy current. We have made a complete classification of that as well, and one of them should be the JKM ambiguities, which also will come from here. Now, reparametrization covariance. So I took this gauge, fixed this gauge, but there are certain coordinate transformations which I can do will also keep me in this gauge, but will change the way I slice the horizon. Now what happens to this entropy current? So I could have started with this gauge and obtain an JV-JI. I could have started with this gauge and have obtained a JV and JI from there. And how do they transform under this coordinate transformation? So you can see that this equation, this EVV is a rank 2 tensor. So this EVV has to transform the way a rank 2 tensor transforms, which is like this. But this JV and JI transforms in a very non-trivial way. in a very non-trivial way this JV and JI transform, so that there are very non-trivial cancellations, and ultimately, so this is how this JV and JI transform, so that this equation is, you know, the left hand side is a rank 2 tensor. How much? 10 minutes maybe. I will just, okay. So now, as I showed, this entropy current is not an Lorentzian d minus 1 vector. It's a null vector, and that's why we keep writing it like this. We cannot use inverse metric to write some covariant derivative dot j. We don't know that covariant metric, so we are writing it like this. But it's on a null manifold. Now, how does a vector? What is the definition of a vector that transforms under coordinate transformations on the null manifold? I don't know anything of that. Maybe these are the near horizon BMS or Carolean that people are talking in these days. So do those BMS and Carolean transformations, how does that vector, I mean, I'm calling this an entropy current which should be a vector on a null manifold. So we are obtaining how it should transform under coordinate transformations from the entropy production, that equation. But can there be a more symmetry way of obtaining how this current should transform? So we don't know, but probably this should be the answer. Or in a sense, in some sense, are they some of those super translations or super rotations? So I'm not very.
So is this one set of reparameterization you have analyzed, or you have some?
Can there be more general than this? So we are trying to check that. So take this gauge and find out the Lie of that and solving it. This seems to be actually, this is the gauging of the constant boost that I talked about. You gauge that and obtain this. There are some other reparameterizations of xi's and all, but in the V and R part, it seems like they are all that can be. But we have not looked at it, but these are definitely something which one needs to understand. Now, as Onkar was saying, at linearized order there is actually no entropy production. One just shows that the entropy is not destroyed. But you know, Harvey Real and all have gone ahead and have shown that if you go beyond the linear order, the EVV has a structure like this, where this square terms comes with the desired sign, so that the second law arguments will kind of go through. They have done it to, I think, next to leading order and some orders. It's still perturbative. And also they had to use a new perturbative version parameter L, which is the effective field theory setup. So they could do it only in an effective field theory setup. So in 2016, along with Mukund, Loga, we wrote a paper where we could do exactly this thing for Gauss-Bonnet up to all orders in the expansion. But there is some issue with an abstraction term and stuff like that. But Harvey Real and all could avoid that just by adding a new perturbation parameter on top of the amplitude expansion, is the effective field theory expansion.
Only for gravity theory, because matter is not there in this Harvey Real setup?
No. So yeah, so one can check that you can go beyond nonlinear order. Now, I've been talking about the second law. The first law is kind of automatic because world entropy by definition satisfies that. And we also looked at the zeroth law. The zeroth law amounts to looking at not the VV component, but the VI component. The VI component of the equation of motion, the off-cell structure of that, involves del I of x. X was the metric parameter, and del I of x is actually the, x is actually the surface gravity. So a zeroth law proof one can also do along the same line, which we have also done in some sense. Now, I don't know how much time I have, but just to say that there are certain 2 minutes. So I would not go into this. So the Busso bound is a bound which kind of says that you know, the 1/4 of so maybe I can just show it here. So if you have a d minus 2 dimensional surface, you draw a light sheet from there. So this has a surface which has surface area, let's say is surface B, a spatial D minus 2 dimensional surface, and this is B prime. So these are all null generators, congruence of null generators. From a given spatial slice, I choose that surface which has the expansion is negative. Now if there are some matter which can be presumably written as some approximations, some entropy current for that matter, S mu, and then K mu, if that is the null generator on the light sheet, then this defines a local entropy flux on that light sheet. Now that, under some assumptions, will always be bounded by this. So A of B is the area of this surface B, and this is the light sheet that one should consider. And B prime is not written here, is not drawn here, but let's say I cut it down at some future B prime over here. So the total entropy flux should be bounded by the area. This kind of comes from focusing theorem. If you have some matter passing with some entropy over here, there is some energy, so that energy will focus it more. So this area, so there is a limit of two congruence, two null generators before hitting a caustic. So this is the bound, this is the Busso bound, is a like entropy flux in a null surface which is a light sheet bounded from above by the area difference of the codimension 2 slice. We have been able to show that this can be generalized to any arbitrary theory of gravity treated in an effective field theory sense, where this area one can just substitute with the world entropy plus JKM corrections that we have been doing. Now this actually uses some Raychaudhuri equation, as you can see, and then there are equation of motion coming from the higher derivative pieces on top of the Einstein theory, R mu nu, and using them here. Actually I would like to answer to Aninda's question is that in this case it's very important that this S is this quantity S mu K mu, theta is the expansion, on the V is the affine parameter on null surface. So you have a quantity like this. So alpha is my effective field theory parameter. Now theta and sigma has to be order epsilon square in the perturbation. If it is stationary, then there will be no expansion and all. But if I have configurations for which this theta square and sigma square are of the order of alpha square, which comes from here, or alpha square epsilon, which is the epsilon order over here, then there is a issue with the sign. So in that case this Busso bound will be in trouble even if it was satisfying in the leading root GR. So we could look at those problematic terms and could correct it accordingly, so that ultimately this world entropy kind of thing. And this might be interesting even for the non-minimal case, where here there is a clear issue of what to put in the entropy part and what to put in the geometry part, entropy of the matter, but then we see for non-minimal coupling matter entropy and the gravitational entropy gets interlinked. So this is how we kind of proved the Busso bound, modified the Busso bound that was known for the root GR theory. So these are some future directions.
Or again in some kind of perturbation theory, that fact that we got the Busso.
So it's a result in perturbation theory, but it will work to all orders in perturbation theory. Perturbation parameter are the epsilon. So I was worried about the sign of this sign. I wanted it to be negative. Now these came with the parameter of order epsilon square, because this theta and sigma, there is no alpha present here, and the other was alpha.
Epsilon, sorry, is just the deviation from stationarity.
Deviation from stationarity.
But it's a proof to all orders in epsilon.
The problem arises only in the leading order in epsilon, or epsilon square. Once you cure that, you see that it works to all order in epsilon and sigma.
Is it because the higher order will be subleading?
Higher order will be subleading.
The higher order is subleading.
But and there will be no problematic contributions from there.
But but isn't there a situation where the, say, order epsilon piece is giving you 0, so to check the sign you have to go to epsilon square?
Yeah, I think that's
The-
you have to do that, yeah.
Yeah, so then that's, if you're claiming to all orders, then, right?
Meaning, I mean, if there is no order epsilon, if you are looking at a stationary configuration, this bound is saturated.
No,
That
but
means
what
it's
is
0, right?
order epsilon square? That's what it's specific.
So this theta and sigma are epsilon square order pieces, because if you, this theta is like 2 derivative of, theta is a del v, twice del v, so it's an order epsilon square pieces. So you are actually comparing theta square with alpha square EVV-HD. Now EVV-HD, from the boost weight analysis, you can show that for stationarity, this EVV will also be 0. It's a positive boost weight quantity or something. But once, if you have configurations which are like this, then you have a worry. Once you cure that with adding something on both sides, where this Q is actually that JV and JI piece which we had over in EVV, once you cure that, you see this term is order epsilon square and this term is alpha square epsilon square. So it can never dominate this term.
What is alpha?
Alpha is the effective field theory.
No, what does that mean?
Well,
Dimension term is something else.
yeah. So I have a root GR plus alpha square R square, let's say.
Okay, so you are proving it, taking the higher derivative terms to be parametrically small. Which
Yes.
I understand. And then you're saying that that term has to be smaller than the leading term.
So initially there was a problem if I don't have this QQ piece over here, because this was alpha square epsilon and this was epsilon square. But what I've done is I've taken out the order epsilon piece and added it to the geometry side, which was actually what we were seeing even for the non-minimal case. Then this will always be epsilon square alpha square, and it can never dominate a epsilon square if epsilon is of the order of alpha, which we wanted from here. So we figured out one problematic configuration where we have to be careful once we cure that, and that cure is also not something just coming from here. It's also well justified because area has to become world entropy in higher derivative theory. That also naturally comes out. Sorry, for going over time, but yeah.